Hello physics students. So in this gravitation part 2, this spherical Earth, we learned that the force of gravity gets weaker the further you get out from planet Earth, and that the direction changes as you go around Earth. And in the last video, we studied one consequence of that, a unique kind of motion, a kind of projectile motion, where you fire something fast enough in the sideways direction, and if you shoot it at just the right speed, it will fall forever and go in an orbit, a circular motion. So we were able to calculate exactly how fast you had to shoot something and also how long it would take to go around. So that was for shooting things sideways. Today, we're going to now think about and discuss and study the motion, the types of motion that are possible when you throw something not sideways but straight out. Now, it turns out that a lot of people have ideas about shooting things straight up that are quite wrong. Like you may have heard the expression, what goes up must come down. I hate that expression. It's wrong, but the reason why people think that is because when they throw something up at a, well, let me do it a little bit lower, at a gentle speed, an object rises a certain amount and then comes down. If they throw it harder, it rises higher, but it still falls down. And if you go outside and throw this as hard as you can, same thing. It just goes even higher still, but it always comes down. And so people think, well, it's true for my arm. It must be always true. And we're going to see that that's not true. In fact, you can calculate the speed at which you have to throw something so that it goes up and never comes back down. So that's the topic for today. What is that speed? How do we calculate it? It's called the escape speed, and I'm going to use the symbol V with a subscript E. So here's a diagram, the Earth, upward projectiles. Projectile A, I launch it up at some speed. It goes upward into outer space because I'm throwing it fast enough. It's beyond the atmosphere. It's decelerating because gravity's pulling it back inward, right? So we know that. It's going to slow down. If you're moving in the opposite direction of the force, you slow down. Slow down, you eventually stop. And then gravity keeps pulling, so you fall back in. But that's only because the velocity of particle A, projectile A, was less than this escape speed. So it goes up, comes back down, and note that when it lands, if I shoot it up with 5 meters per second, it hits with 5. If I shoot up with 1,000, it hits back with 1,000. So that's what this is saying. Of course, we're ignoring air resistance. Now, let's suppose that I then launch something even faster, as we saw with a tennis ball rising in the screen, but now I'm shooting it faster. It's into outer space. It rises even further than A, but it's still decelerating because gravity is acting this way. And so it goes higher because of the larger initial velocity. And then up here, it's got a velocity of 0, and it's pulled back and accelerates and comes back and hits the Earth, once again returning with the same velocity. But it goes higher and returns. So again, what goes up must come down? No, because here's the thing. If I launch this just fast enough, it'll keep rising and slowing down, decelerating. But eventually it'll get so far from Earth that the force of gravity, as we know, right, as I said right at the start, the further you go, the smaller the force of gravity gets by that formula, Fg equals capital G m1 m2 over r squared. That formula says that the gravity force, the attraction between this projectile and the Earth, gets smaller and smaller. If we achieve a very large distance from the Earth, in other words, infinite distance, the force of gravity becomes 0, and there's no more pull. And so the object never falls back down. What goes up must come down is like literally saying the Earth is flat, and gravity never gets weaker. It pulls all the same, no matter how high you throw. Not true. So this case, V of particle C is greater than or equal to the escape speed. The object goes up, never comes down. It has escaped. Okay? Now, what is this escape speed? Oh, so let me create a pause, allow you to copy this down. Okay, so what is this escape speed? How can we calculate it? It turns out that to calculate this, we need a formula for the gravitational potential energy that's beyond the course because it involves calculus and deriving. So I'm not going to put that up there, up on the board, obviously, because not part of the course, and this course is not calculus-based. I'll give you the answer, the formula that's derived. Here it is. The escape speed of anything is given by this formula. 2 capital G being that constant on the reference table. Uh-oh, I left my reference table upstairs. But you know, it's the front cover of the reference table. This is the mass of the planet you're trying to escape, and this is the radius of the planet you're trying to escape. And there's a square root there. So what is the escape speed for Earth? In other words, how fast do I have to throw this up so that it goes up and never comes out, goes deep in outer space, beyond Saturn, beyond Pluto, and it just keeps going into outer space. So we start with a formula. Then we plug in capital G off the reference table with the units, the mass of planet Earth, and the radius of the Earth. So a note, if I try and trick you and I say I have a 0.02 kilogram tennis ball that's a radius of 0.03 meters, what's the escape speed? Don't get tricked and put that mass of the tennis ball here and the radius of the tennis ball here. No. The mass of the object you're throwing, irrelevant to the escape speed. If I'm shooting this up or a school bus, it doesn't matter. I have to throw them both at the same speed to escape. The mass of the projectile doesn't matter. It's the mass of the planet, radius of the planet. Boom, plug it on a calculator, 11,291 meters per second. Incredibly fast. So let me comment about that in a second. Let me give you a chance to copy this down. By the way, you should also practice this on a calculator. Make sure you can get this because, like I've said in previous videos, some of these big and small numbers and dividing can be easy to mess up the order of operations. Make sure you can get this. That turns out to be, if you do a simple conversion, to 7 miles in 1 second, or 25,000 miles per hour. So if I could throw this up at 25,000 miles, well, obviously I can't. The fastest pitcher in Major League could throw like 100 miles an hour, way too slow. We need rockets and all these kinds of things to achieve these speeds to escape. So that's why, you know, with our arm, we think what goes up must come down. Now, if we were in class, I would show some beautiful clips of Apollo 13, the movie. And I have a model of the rocket, a plastic model. It's like, you know, maybe like, well, taller than what we could see on the screen, but maybe it's like this long with all the stages and the parts that come apart. And I would show you just how much energy and rocket fuel it takes to launch 3 astronauts, just 3 astronauts into outer space and escape the Earth. It's mind-blowing. It's like a skyscraper of fuel to get 3 people in a small capsule into outer space and escape the Earth at this speed. But I won't show it because I'm going to post this on YouTube, so I would be probably violating copyright laws. So, I can't show you the video. I could just kind of comment on it. But enormous amount of energy to get very little mass to escape. That's why it's so hard to escape. So that's the first thing. But I now want to talk about some implications, some very fascinating implications of this idea that there's an escape speed that you need to escape planet Earth. You may not have ever thought about this, or maybe you have. Why do we have an atmosphere and the moon doesn't? Or other small planets don't have really an atmosphere? Why is that the case? And people think, well, it must be like some kind of membrane, like a rubber. No, obviously not, right? It's just the atmosphere, and then there's outer space. And it has everything to do with this concept. So as you know, the air molecules in a gas are constantly moving. They're zipping around. The oxygen atoms are crashing into me, bouncing off. Nitrogens, CO2, they're all flying around. And you also know that the hotter that the gas is, the faster these little atoms or molecules are zipping around. So you can actually calculate, and if you take chemistry in college, you'll have to do this, the speed of an average molecule in a certain temperature, at a certain temperature of a gas. It turns out that I calculated the speed of an oxygen atom let's take a really hot temperature in the desert. It's 100 degrees. So we're really hot and the oxygens are moving faster in the desert than they're in this room or in the North Pole, for example. So you could calculate and you would get that the oxygen atoms at 100 degrees Fahrenheit are going about 490 meters per second. And because of that, what that means is that they're zipping. Some of them are going up, some of them are going sideways, some of them are going down. The ones that go up are not going faster than this escape speed, so they go up into outer space and they get pulled back down and they get stuck to Earth. So those gas molecules are constantly flying outward and falling back in. Gravity alone is why we have an atmosphere. So that's one of the fascinating implications of escape speed. The speed of oxygen, 491 to 400, that means Earth has an atmosphere. Now, of course, you'll also learn in advanced chemistry courses that that's the average. There are some molecules of oxygen that are going even faster than that, quite fast. And so on the moon, what would happen is if you let go oxygen, when the sun hit it, those oxygens would be going so fast from the sunlight that they'd go whoosh, and they'd be going faster than the escape speed, and they'd go right up into outer space, and the moon would lose that oxygen. It doesn't have enough gravity to keep it in. It escapes from just the thermal effects. So fascinating. You need a small enough temperature and enough gravity to keep the atmosphere around the planet. So the other fascinating thing, I find it fascinating and scary, by the way, is that, when I said I launched something up at 10 meters a second, it comes back at 10 meters a second. Well, if I launch something at 11,291 to get it all the way into deep outer space, that means that if it comes from deep outer space and hits, it'll hit with 11,291. So this happens to be the minimum impact speed of any asteroid. It's coming in that. Now, of course, if I drop something from deep outer space and it sort of creeps toward the Earth and eventually crashes into the Earth, it's this. But if it's already moving in outer space, it'll hit even faster than this. So this is the minimum impact speed of any rock coming from outer space. And so it's kind of frightening to think of these things coming in that fast. And you've heard of, like a meteorite that came and possibly destroyed the dinosaurs, made them extinct. And so, you know that this is possible. But it's an interesting idea to think, well, how big of an asteroid would it take? Okay, now, in Hollywood, when you watch movies, not surprisingly, they always have the physics way wrong. Like I've seen movies, I think it was Deep Impact or Armageddon, I don't remember which one, it was a movie back when about an asteroid hitting, and they said, an asteroid is coming to hit the Earth and it's the size of Texas. And so, everybody thinks that's scary because it's a big giant state. But what I'm going to do is calculate the exact size of an asteroid, how big it would have to be so that when it comes in this fast, it would deliver the sufficient amount of kinetic energy to create like an atomic bomb blast with the kinetic energy. I think you'll be surprised. Okay, so let's go ahead and begin that calculation. Okay, by the way, I don't know if I create a pause, so if you need a moment, then copy this down. Okay, so you could look this up online, but the kinetic or the energy of the bomb that exploded on Japan was about, I'll say E for energy, was about 6 times 10 to the 13th joules. And you've probably seen the pictures in history class. One bomb lands with that energy, the city was gone, vaporized, people gone in a split second. So you know that's a devastating amount of energy. Well, what we could do is we could say, all right, let's suppose the asteroid comes in and it's going to come in with that amount of kinetic energy. And whether it's an atomic bomb blast or kinetic energy, it's the same thing, it's energy. It would be just as devastating with the kinetic energy that whaps into a city, okay? So let's plug that in. And say m is unknown, but the speed that that asteroid is going to come in is the escape speed, because like I said, coming in, it'll come in with the same speed as if it were escaping. And you solve for m, and you would get about 941,000 kilograms. Okay, that sounds bad, right? That's a lot of kilograms. But what does that mean? Can you visualize 941 kilograms, 1,000 kilograms? Probably not. So what I'm going to do is now figure out the volume and the size for a likely material that might hit. A lot of these asteroids are made of iron. So let's suppose it's a chunk of iron that's this massive. We could, from the density of iron, figure out the volume of the iron. D equals mass over volume, you learned, okay, earlier in a science course. The density of iron, oops, I forgot it, was 873, or is 873 kilograms per meter cubed. So we have 941,000 kilograms over the volume. And we could do a little algebra there. And that comes out to be 1,078 meters cubed. Okay. So if you need a moment, I'm going to create a pause to allow you to copy this down. Moving on. Can you visualize that volume? I can't. So the last thing I'm going to do is calculate the size. Let's suppose this iron coming in with the kinetic energy equal to an atomic bomb blast is a sphere. Likely, right? It's some kind of round shape. So the volume of a sphere is 4/3 pi r cubed. If I take that volume and r is unknown, and I do a little algebra, multiply by 3, divide by 4, divided by pi to get those to the other side, and then take the cube root of both sides. What I would get is approximately, ready? 6.38 meters across. Double that for diameter. No, that's the radius. Double that for diameter. You get about 12.7 meters across. Feet-wise, that's about 40 feet. So let me create a pause, allow you to jot that down, and I'm going to comment a little bit more. All right, so 40 feet is not that big. It's probably the size of a typical classroom. Imagine a meteorite the size of a classroom comes in, strikes a city, poof, city's gone. Okay? Remarkable. It does not take much size because of the enormous velocity of these rocks coming in and slamming into the earth. Now, the Hiroshima bomb was a small bomb in terms of atomic bombs. I was doing a little research, and there were very quickly new bombs developed that had like over 1,000 times the explosive power. There was one detonated that had 4,000 times. In other words, it was like 4,000 Hiroshima bombs all in one pile, all at once. Well, those aren't the most common. Most of them are about 1,000 times. So the biggest bomb that the United States ever exploded was 1,000 times, or 6 times 10 to the 16th joules of energy. If you repeat this calculation, I won't, I'll just give you the fun part at the end. What you get for a diameter there is 127 meters across, which is about 400 feet. So, you could picture a football field in your head, right? So imagine an asteroid coming, a meteorite coming out of the sky, falling from outer space. That's a football field in size. Hits New York City, all 5 boroughs are gone, disappeared, vaporized. Just a football field across. Incredible, the devastating power. Now, I also looked up, well, how many nuclear bombs are on planet Earth? Everyone knows that if there was a nuclear war and we all bombed each other, there'd be nothing left, right? It's enough to destroy the Earth, destroy life, okay? Or most of it anyway. So we know that's a lot of energy. And I came across a figure that estimates there are about 6,000 of these bombs for all humanity that people have. So if you figure out the energy of all the world's nuclear weapons, you would do this. Multiply 6,000 times that. And when you figure out, do this calculation, the size of an asteroid to deliver that much energy, you get 1.5 miles across. So, I'll create a pause. You could just jot this little information down. So asteroid the size of Texas, like they say in the movies? Not at all. A tiny speck. If you look at the globe and you do a simple ratio to figure out on this scale how big of a rock it would be, it comes out to be less than 0.07 millimeters. 0.07 millimeters would be like much smaller than the period at the end of a sentence in a book or a piece of paper. Imagine something, a tiny fragment of the period at the end of a sentence coming toward the Earth. If you're looking at it from here, you're like, oh, it's a tiny thing. That has no effect. It's so little speck coming toward the Earth. That hits the Earth. It's like the energy of all the world's nuclear weapons combined in one pile, lit off, explodes a giant hole, destroys civilization. And you could read about what kind of damage that would create. It's pretty frightening. And the other thing is, then you ask yourself, if such a small rock could hit the Earth, create that much damage because of the impact speed, how likely is this to happen? Well, if you're into this sort of gloom and doom stuff and you like things like scary movies, you could go just Google, asteroid nearly hit Earth. You'll see article after article. And you know what the common theme is? Always the article says, yesterday, it's the news story today, yesterday a rock passed and no one knew until it passed. And it's like, no one has any idea. And then, whoa, there's a rock. It almost hit us. It's pretty scary, pretty frightening. And another thing that I would show if it were in class, there was a video, National Geographic, about these asteroid impacts, which again, I can't show because then I'd be violating copyright. But there was one really scary part of the film. And there's this physicist, just this nerdy kind of guy, older guy, and he's sitting there and he looks into the camera and he says, and the first time you're going to know when that rock is coming, most likely, is when you see the fireball swallow up the horizon and the fire's coming at you. And I thought, oh my, that was so scary. So fascinating stuff, scary stuff about these rocks. Obviously, they don't hit often. The last one hit millions of years ago, maybe. But it is something to think about and interesting. And it's all about this escape speed, the enormous speed you have to throw something to escape, which is then also the speed it comes in when it hits. That creates an enormous amount of kinetic energy for not much size, not much mass to deliver a terrifying blow to planet Earth. All right, so a little dark, but it is part of the physics that we studied. I hope you enjoyed the video, and I'll see you in the next physics video.